So, what on Earth does a falling apple have in common with the moon orbiting the Earth? Well, the answer is this single beautiful rule that runs the entire cosmos: Newton's law of universal gravitation. Today, we're going to dive deep and break down this fundamental law, the one that connects everything from tiny objects on Earth to the biggest galaxies out there.
All right, here's our game plan for this explainer. We're going to start with Newton's big idea of a universal pull. Then we'll get into the weeds of that mysterious gravitational constant, g. After that, we'll actually prove that gravity is always an equal and opposite force. And finally, we'll crunch some numbers to see it all in action.
Okay, let's start with Newton's profound insight. Before him, people thought the heavens and the Earth were two totally separate places with their own set of rules. His stroke of genius was realizing that a single force was in charge of both.
Now, this might seem pretty obvious to us today, but you have to understand, back in Newton's time, this was a huge deal. The idea that one single predictable force could explain both a boring old apple falling and the majestic motion of the moon, that was absolutely revolutionary. It's the whole reason we call it the universal law.
So here it is, the formal statement of the law. I know it looks like a mouthful, but don't worry. It's really just built from two pretty simple ideas, and we're going to unpack them right now. The first piece of the puzzle is all about mass. It's super intuitive. All it means is that the more massive the objects are, the stronger the gravitational pull between them. Think of it this way: more stuff equals more pull. Simple as that. If you double the mass of one object, you double the force.
Okay, next up is distance, and this is where it gets really interesting. This is the famous inverse square law. It means that as you pull two objects apart, the force between them doesn't just get weaker, it absolutely plummets. This super dramatic drop-off is one of the most critical features of gravity.
So when we put those two pieces together, the pull from mass and the massive drop-off with distance, we get this complete relationship. The force is proportional to the masses multiplied together, all divided by the distance squared. We are so close to the full equation now. To turn that relationship into a real, honest-to-goodness equation we can actually use, we need one more thing: a constant of proportionality. And that is g, the universal gravitational constant. It's kind of like this secret ingredient that scales the whole relationship to perfectly match how the universe actually works.
So what is this g all about? Let's take a minute to really decode this fundamental number that's woven into the fabric of our cosmos. Here's its value. And just look at that exponent, 10 to the power of -11. That is an absurdly, unbelievably tiny number. And that right there is the key. This is why gravity feels so weak in our everyday lives. The actual inherent strength of gravity is incredibly small. So let's quickly review the most important things about g. First, it's a scalar. It's just a number, no direction. Its incredibly tiny value is the reason you don't feel a gravitational pull towards your desk right now. It's also universal, meaning its value is the same no matter where you are in the cosmos. And crucially, it doesn't matter what's between the two objects. Gravity works right through it. All right, now for something really cool. If we look at the directions of these forces, we can actually prove that gravity perfectly obeys Newton's third law of motion. For every action, there's an equal and opposite reaction. Okay, first let's write down the force that mass 1 exerts on mass 2. We'll call it F21. The first big chunk of the equation gives us the strength of the force. And that little r hat at the end, that's just a unit vector. All it does is tell us the direction of the force, which in this case points from the first mass towards the second. Now, let's do the exact same thing for the other force, the one mass 2 exerts on mass 1, or F12. The structure of the equation is identical, right? But notice the direction vector is different. This one, r hat 12, points from the second mass back towards the first one. And here's the simple, elegant connection. It's just geometry. These two direction vectors point along the very same line, but in perfectly opposite directions. In math, we show this by saying one is simply the negative of the other. And this leads us to a brilliant conclusion. When we substitute that relationship back into our equation, we prove that F12 is the exact negative of F21. The forces are equal in strength and opposite in direction. It's a perfect action-reaction pair. The Earth is pulling on you with the exact same force that you are pulling on the Earth. Pretty wild when you think about it. Okay, we've got the theory down. Now let's make it real. By actually plugging in some numbers for real-world scenarios, we can get a much more intuitive feel for how gravity really behaves. Let's start with a quick little thought experiment. Based on everything we've just covered, take a second and think. If you double the distance between two objects, what happens to the force? The answer is it becomes 1/4 as strong. It doesn't just get cut in half, because the force depends on 1 over the distance squared. When you double the distance to 2r, the denominator becomes 4r squared. The force just falls off a cliff. This powerful drop-off is key to understanding gravity. All right, let's do a full calculation. Let's find the actual gravitational force between two students. We'll say one is 50 kilograms, the other is 60, and they're sitting 2 meters apart. Now all we gotta do is plug these numbers into Newton's equation.
And the result is about 5 times 10 to the negative 8 newtons. That's a decimal point followed by 7 zeros, then a 5. It is such a mind-bogglingly small force that it's completely unnoticeable, totally overwhelmed by everything else. This right here is the definitive proof of why we only feel gravity from something gigantic like a planet.
So let's just quickly recap the absolute must-knows. The gravitational force gets stronger with more mass, and it gets much, much weaker with distance, specifically the square of the distance. We can wrap all of that up in the beautiful equation F equals g times m1 m2 over r squared. And always remember, this force is a mutual two-way street, a perfect action-reaction pair. And this leaves us with one final fascinating paradox to chew on. We've just proven that on a human scale, gravity is astonishingly weak, almost comically feeble. So how is it that this same weak force is the grand architect of our entire universe, the one responsible for building planets, stars, and whole galaxies? The answer lies in its unstoppable reach and the fact that it never, ever pushes away. Thanks for joining me.